Hi, welcome to this lecture on Universal Approximation Theorem. If you have worked in machine learning, you may have heard of this. Otherwise, you may be hearing about this theorem for the first time. This lecture is an attempt to illustratively prove this theorem. And my understanding is that if you truly understand Universal Approximation Theorem, you have a very good intuition for why machine learning or neural networks are able to do such powerful things that it is capable of doing. So technically, this is not in the strict sense, this is a proof, but this is more like an illustrative demonstration or a way for you to be convinced of the validity of this theorem. So my name is Dr. Sridhar Panat. I'm a PhD from MIT. And in this lecture, we'll be going through this theorem with a very specific example. So let's get into the lecture. Universal Approximation Theorem states that a feed-forward neural network with just a single hidden layer, and this single hidden layer will just have finite number of neurons or nodes, and this kind of a neural network can approximate any continuous function within a range or a subset of input values. So this function will have set of inputs. But a neural network which is of feed-forward nature and single hidden layer and finite number of neurons in this hidden layer can approximate any continuous function within a subset of inputs to any degree of accuracy, provided the activation function that we use in this feed-forward neural network is non-constant, it is continuous, and it is bounded. There are so many different terms here, and that's the reason why I have made most of them, or most of the important ones, in bold and underline: feed-forward neural network, single hidden layer, finite number of neurons, etc. So don't be overwhelmed if you cannot visualize this theorem really well. Basically, in simple sense, what it is saying is, using discrete set of items, you can kind of approximate a continuous function or anything that is continuous, and the degree of accuracy will depend on how many discrete items you are chopping this whole thing into. You may be familiar with this idea if you have done integration, numerical integration, as you can see in this picture. But what the Universal Approximation Theorem is saying essentially is something like this. You can think of neural network as function approximators. And let's see if this is true. Let's see by taking a very specific example. So, Universal Approximation Theorem has been stated by many people, and this is Ian J. Goodfellow. He was formerly at Stanford and DeepMind, and he is a very, very big name in the machine learning community. And he also has stated that a feed-forward neural network with a single layer is sufficient to represent any function. And by any function here, it largely means continuous functions. The size of the layer may become infeasibly large if the function is very complex, and it may fail to learn and generalize correctly if the size is very small. But basically, this a feed-forward neural network with a single layer is sufficient to represent any function. And there are many famous such quotes, but our goal is to try to understand the intuition that all of these people had when they were stating this theorem. So let us consider this continuous function. This is a very simple function, y equal to x cube minus 3x square plus 2x plus 5, like a cubic equation, basically. And here we have plotted the range from x equal to minus 2 to x equal to 4. That's the range we have plotted. And y looks like it approximately goes from minus 20 to plus 30, roughly. So we can, if we consider these set of straight lines, so these are a bunch of straight lines, red, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have made 11 straight lines. Some of them are solid lines, some of them are black dotted lines. And if we overlay this on top of the function that we saw earlier, we can see that these lines, these set of lines, approximate the function very well, as if it's like a piecewise linear function. And the more the number of such lines, or the more the number of divisions to which we've chopped the range of this function, the x range of function, the better and better this piecewise linear approximation will become, right? So this is obvious to see, and you can also already imagine this. This is not at all something that is surprising. Now the question is, how can we mathematically represent these lines? This is a very tricky question. It's not trivial. You may think that, okay, I can easily calculate the equation of each of these straight lines piecewise individually, and I can represent my whole function as a piecewise function. But let's say I don't want to represent it as a piecewise function, because in piecewise linear functions, the equation of this line is y equal to, let's say, 0x plus 5. And the equation of this line may be y equal to something else. But it's valid only in that range. So here y equal to 0x plus 5 is only valid in the range of x equal to 0 to x equal to 1. Outside of that, it is not valid. But I want to be able to write a function where I don't have to look at the range within this current range that I'm looking at. So currently I'm looking at -2 to 4. I don't want to chop it up any further when I'm defining my function, right? I want a function that can look like something like this, or any other function, any other continuous function. And I don't want to use a piecewise linear function, although the outcome may look like a piecewise linear function. If you are not clear what this means, I'll show you in a moment. So consider this very fascinating yet simple function, ReLU, rectified linear unit. You may have heard of this already if you're familiar with machine learning and neural networks. And ReLU is nothing but ReLU of x is max of 0, x. So what does this mean? If x is positive, the max of 0, that positive number is x itself. So if x is greater than 0, the value of the function is y equal to x. What if x is less than 0? That means max of 0, any negative number is 0 itself. That is the maximum value, which means the value of ReLU of x would be 0 for all negative numbers, and it will be x itself for all positive numbers. So this is a simple version of the ReLU function. Now there are many different types of the same ReLU function that we can construct by modifying the sign of the ReLU function or adding like a constant to the x. Let's see how we can accomplish different types of ReLU functions using the basic same idea. So this is a platform called Desmos, and we can plot any kind of functions here to visualize them. I'll be sharing the link to this in the description. So I highly recommend you to check this out. So this is the normal ReLU function. So here I have defined f1, f2, f3, etc. up to f6 different functions, but I'm only plotting one of them, which is the normal ReLU function here. And you can see that for x less than 0, it's the value is 0. For x greater than 0, the value of y equal to x. Now, can you look at this? Let's say y equal to ReLU of x minus 1. Then what that means is, for all the values from negative infinity till x equal to 1, the ReLU, the value of this is 0, which is, as you can see by seeing this red line. And for all value of x greater than 1, the ReLU is basically x minus 1. So if x is 2, the value of this function f1 is 2 minus 1 equal to 1. So this is like a ReLU that is offset by 1 unit to the right side, right? Now what if I visualize this f3? f3 is ReLU of x plus 1. So ReLU of x plus 1 is nothing but the original ReLU offset by minus 1 in the negative x-axis direction. This is fairly easy to understand, I hope. Okay, let's look at y equal to 2 times ReLU of x plus 1. So now what will happen? The ReLU of x plus 1 was this purple kind of line. The slope of that in the values where the y-axis value is positive will become double, because now the function is 2 times ReLU of x plus 1. That's why this orange line will have twice the slope of this purple line. How about minus ReLU of x? So ReLU of x is this green line, right? And minus ReLU of x will be like a mirror image of that, where the x-axis will act as the mirror. So for all negative values of x, the value of this will be 0. For all positive value of x, the value of negative of ReLU of x will be minus x. What about this? Minus 3 times ReLU of x plus 2. So this will be the normal ReLU. It will be offset by minus 2 in the x-axis, so negative axis direction. And the slope will be minus 3. So this slope is actually minus 3. So it's not, so if I keep it that's minus 1, then you can see that the slope is minus 1. If I keep it minus 0.5, slope is again increasing. It's basically going in the magnitude is decreasing, but the value is increasing. And if this is 0.5, then the slope will be, if this is plus 0.5, slope will be positive and its magnitude will be 0.5. So this is how we can manipulate the constant outside of ReLU and the numbers associated with the X. And we can get different types of ReLU. We can shift it, we can flip it downward. We can also have ReLU whose definition is something like this, ReLU of minus X. So let's plot that. What about this? ReLU of minus X. How would this look like? Let me not plot anything else. ReLU of minus X is exact. You can see that it's a mirror image of ReLU of X, but this time the mirror is not X-axis, the mirror is Y-axis. Right? So, and what if now it is minus X plus 2? X plus 2. Then what happens is you are now shifting 2 units to the right. If it is minus X minus 2, it will be shifted to the negative side. So there are so many different functions that we can construct using this simple combination of linear functions. ReLU is essentially linear in its positive range, but 0 in its negative input range. But using this, we can construct so many different types of piecewise linear functions. So now what we will see is, for the function that we were considering, we can see how to construct combinations using these ReLU. So what we want to first try is, let's try to add and subtract the ReLUs to see what is the result that we can get out of it. So can we add some 2 or 3 different ReLUs to see if we can get some other shapes which are not really possible using normal functions? Let's see that. So have a look at maybe just these 2 functions. Okay, let's take ReLU of X. So this green function is ReLU of X. And let's also take maybe ReLU of minus X plus 2. And what we could do is we can define a 7th function, f7 of X. f7 of X equal to maybe I can say that this is f5 of X plus f6 of X. We can see what this looks like. This may not look like much. If there are spaces over here, it will not work. So I have to delete any white spaces. Yeah. And there is a white space here. Okay. So now you can see that the function looks something like this. The slope is completely negative in this range. In fact, it's always negative, the slope of this function. We can also do something like, so you see this one, this function this triangle-like structure which I got. I can open this and I can have a look at it. So here, let me first not display anything. First, let me display just the normal ReLU. So this is the normal ReLU function. And if I shift the ReLU by 2 units to the negative axis, x-axis, it will look like this. If I have another ReLU, which is minus 2 times ReLU of X minus 2, it means the point where the value of the function transitions will be X equal to plus 2 and the slope will be minus 2. So then this green line is the F2 function. And now F3 equal to F1 plus F2 will be nothing but this black color. So let me mask everything else. You can see that here we are now even able to create this triangle-like function. And this shape is coming purely as a result of combination of 2 different ReLU functions. So this is how we can use combination of ReLU functions to create whatever we want. So far, I have not showed whatever. I'm just showing a simple structure, simple function here. But now let's come back to our example, because our example was a complex function, right? It was a cubic equation. Let's see how we can approximate that cubic equation using bunch of ReLU functions. So we have a cubic equation which can also be represented using these piecewise linear functions. So if somehow these piecewise linear functions could be created using a set of ReLU functions, that would be awesome, because then ReLU, as you know, are used as activation functions in neural networks, which means this whole function we can potentially represent using neural network. So we will see how to do that. So first, let us try to find the ReLUs that make up this function, right? So let's see that. So let us plot the function that we are looking at first. This is x cubed minus 3x squared plus 2x plus 5. So this was the original function that we were trying to approximate, x cubed minus 3x squared plus 2x plus 5. And let us plot like a normal ReLU first. This is how a normal ReLU looks like. And you might think that the axis, the tangent or the slope is not 45 degree, but it's actually slope is 1, because here the y-axis range is from minus 20 to 30, but x-axis range is only from minus 3 to 5 in this particular case. So that's why it appears as though the slope is not 1, but in fact it's 1. Okay, so clearly this ReLU is not sufficient to do anything. So let's add another one. Maybe I can define something like this. Let's say f1 of x equal to, so I want to shift the ReLU to the left till such that the transition point is from minus 2 to minus 1. So how do I shift the ReLU to negative direction? I can say I'll use capital R. So it's capital R of x plus 2, right? Okay, now the ReLU shifted to minus 2. But the slope is still not good enough. So maybe what I can do is, let's say the slope, I want to keep the slope to be similar to whatever the slope of this guy is. So the slope of this guy is, when the x is changing by 1, the y is changing by 20. So I would say the slope is 20. So maybe here I'll multiply this by 20. Now what's the problem here? This is not really the ReLU that we are looking for. So what I can do is I can define f maybe final. So I'll just say f final equal to minus f final of x equal to minus f1 of x. I'll tell you why we are doing this. So f final of x equal to minus f1 of x. I am not sure if this is being displayed right now because there are some empty spaces. Okay. One more thing that I can do here is, let's say, okay, probably what I should do is, like, instead of this blue line, I should shift the blue here and make the slope to be like this, right? So minus x, what if I had something like this? Minus x minus 2 or minus 1, and the slope was minus 20. How about this? Then this part is approximating the function really well, right? So this looks good. The transition is happening at minus 1, and there is a straight line over here. I can also divide. I can also use 2 ReLUs here instead of 1 ReLU, but for now this looks fine. Okay. Okay, let me also define another new ReLU function, f2 of x equal to, now this time I want the transition to happen at x equal to maybe 0. So, and the slope I want to be, the x value is changing by roughly 1 and y value is changing by 5. So the slope could be 5, right? So I'll copy this, paste it here, and what I will do is this will be 5 and this will be just like that. So this is the pink ReLU, but the problem here is I should not have, actually I should just have a ReLU with plus x, plus 1, and slope is plus 5, and this can represent really well. Now let me see, f final equal to f1 plus f1 of x plus f2 of x. What if I display only f final? Do you think I'm able to approximate? Let me also change the color so that you can see it properly. So the green is my final approximation, final meaning from the range minus 2 till 0. So this green line is now representing my original x cube minus 3x square plus 2x from this range of x equal to minus 2 till x equal to 0. Okay, now let's come back to our business. So we have, if we just look at the function, now our next transition is happening at x equal to 0, right? So our f, the final f is now looking like something like this. Let me see, final f is looking something like this. And I want the slope now to be roughly, so this one has how much slope? X is going from 0 to 1 and y is going from 5 to 10. So the slope of this part is 5. So I want to add something with slope maybe minus 5 so that I can kind of negate this part and create something with slope close to 0. So what I will do is I'll define a function f3 of x equal to minus 5 times ReLU of what? It should be x minus 1 because I want to shift the ReLU. I want to shift the transition point from, actually it should be transition point should be at x equal to 0 itself, I guess. So let me put it this way and let me give it a green color, sorry, different color other than green so that it looks different to you. So it could be blue color. Done. And now if I define the f final as f1 plus f2 plus f3 of x, f3 of x, you can see that now the green line is very nicely approximating. Let me block this blue. Now this green line is approximating this curve very well from minus 2 all the way till, even I would say it's even approximating till plus 2. Somewhat. I'm not saying it's exact, but to great extent, because we are only using so many divisions. If we divide it even further, it will be good. Okay, now what should happen to this green line? The green line has slope 0 right now. Its slope from the point of this x equal to 2, it should transition from a slope of 0 to, how much is this? X is changing by 1 and y is changing by 5. So again, the slope should become 5. So what can I do? I will define a function f4 of x, where f4 of x equal to, what should be my slope? Slope should be 5, right? 5 times r of what should x plus, it should be x plus 2. Sorry, x minus 2. So that the thing is shifting all the way till the transition point happens at x equal to plus 2. So now this is this white line and let us add this onto our final. So now f final will be this plus f4 of x. You see, it's beautifully representing now. I'll hide the white line now. Now the approximation is going reasonably well till x equal to 3. Now we are covered from x equal to minus 2 all the way till x equal to plus 3. Now let us try to approximate from x equal to plus 3 all the way till x equal to something like, I think the range here is, let's try till x equal to plus 4. I only care from minus 2 to plus 4. So here the x value is changing by 1, but the y value is changing by how much? 10 plus 10, roughly 20. So the slope here should change from, currently the slope is 5 here, it should change from 5 to 20, which means the slope of the new line that is added after this transition point of 3 should be an addition of 15, right? 5 plus 15 is 20. So if I add a new function called f5 of x, and if the slope of this is 15 times ReLU of, and where is the transition point? Transition point is at x equal to 3. So this will be x minus 3. Then if I add the f5 over here, so plus f5 of x. Now we have the new green line, and let me hide this blue line. Now you see the function is approximated reasonably well. So if I hide my original function, now this looks roughly like my original function, which was x cube minus 3x square plus 2x plus 5. And of course, I'm not approximating really well here, but obviously, as you can see, I have not used that many straight lines. I have only used very little number of straight lines. But as you can see, it's approximating really, really well. But one thing to note here, in my consideration, I only considered the x range from minus 2 till plus 4, minus 2 till plus 4. So if you zoom out, this approximation will not be good for outside that range. So outside this range means less than minus 2 or greater than plus 4. there will be significant diversion between this green approximated line, which is the sum of ReLUs, and this orange line, which is the actual function. Now let us do one more thing. In actual neural networks, when we write ReLU, we are doing ReLU of, let's say, wx plus b. So we won't have something like negative 20. Let's say we don't want this negative 20 or this business outside. We just want it to be ReLU of something, right? Minus ReLU of something else. So we just want addition and subtraction of ReLUs, or we can also write it just exactly like this, no problem. So I can show you how to represent this whole thing. We have 1, 2, 3, 4, 5 functions here. I can show you how to represent these 5 ReLU functions, which is operating to create this final function called f final, how this whole thing forms a neural network. So firstly, let us write this down. Let's get back to our PPT. So we got our ReLU function, find the ReLU that makes up our function. Let me write it down so that you also have the reference when we are referring to it again. So f final equal to, and this is a function of x, obviously, it's equal to f1, which is minus 20 times ReLU I'll just denote by r, just to save some space. R of minus x minus 1, right? Then it is plus 5 times ReLU of x plus 1. Then minus 5 times ReLU of x. Plus 5 times ReLU of x minus 2. And plus 15 times ReLU of x minus 3. Plus 15 times ReLU of x minus 3. So now the range in which this is valid is from x belonging to minus 2 to plus 4. And that too, when I say valid, I don't mean to say that this is perfectly approximating our original function. I'm just saying that the extent to which we were happy. So this is the range in which we'll be generally happy if this function was applied. So this is how we can use bunch of ReLU functions to represent a complex function, or rather a complex continuous function. So how does the neural network look like now? The input is x. So the x is coming into the input node. There is only one input node because there is only one number as the input. There will be 5 nodes in the only one and only hidden layer. Now what will be the values here? So the values, we can go back to our function. So the first node has minus 20 times ReLU of minus x minus 1. So minus x meaning this, the weight over here is minus 1 because it's minus x, and minus 1 is the bias. So this is the bias to the first node, that is minus 1. Then to the second node, it will be, let me just make this small. Second one, it will be 5 times ReLU of x plus 1. So you might be wondering, where is this minus 20 and where is this 5? I'll show you that in a moment. So here it is basically ReLU of x plus 1. So x plus 1 means the weight corresponding to that is 1, right? Weight is 1, and plus 1 means bias is also plus 1. So that will be here. So this arrow is a bias, so don't get confused. It's not something that is going from this node to this node. It's just a bias that is going into the second node. Then we have the third function, which is minus 5 times ReLU of x. So here weight is 1 and bias is 0. Then we have 5 times ReLU of x minus 2. So weight is 1 and bias is minus 2. So weight is 1 and bias is minus 2. Then we have 15 times ReLU of x minus 3. So weight is 1 and bias is minus 3. Weight is 1 and bias is minus 3. Now what about these connections? The weights of these are the coefficients of our ReLU function. So first one is minus 20. Then here it is 5. Here it is minus 5. Plus 5. And 15. Now, can we write this neural network in a functional format? Of course. So here this tilde icon, I'm just showing it to represent our activation function. Obviously, our activation function is ReLU, right? So what would be the output of output that is coming over here, it will be ReLU of minus x minus 1, correct? Minus x minus 1. What about the output of here? That will be ReLU of plus x plus 1. So first one is minus x minus 1. Second is x plus 1. So this one would be, sorry, not that. Before we apply this, the output that is coming out here will be ReLU of x plus 1. What about this one? This one would be just ReLU of x, right? So I'll just draw it here. This will be just ReLU of x. Then this guy would be just ReLU of x minus 2, correct? Yeah, ReLU of x minus 2. X minus 2. So please don't get confused. I think I'm confusing you by using different notation. So when I say RE, I just mean ReLU. I don't mean real number or anything. So just please don't get confused. Then the final one would be ReLU of x minus 3. This one. So ReLU of x minus 3. I think that is what it's here also. Now, what happens here in this summation? What happens is this thing gets multiplied by minus 20. Then this thing will get multiplied by 5. This will get multiplied by minus 5. This will get multiplied by 5 and this by 15. And then you will add all of that. So what is the result? So minus 20 times ReLU of minus x minus 1. So approximation of f of x, maybe f approx is equal to minus 20 times ReLU of minus x minus 1 plus, what is this? 5 times ReLU of this is this guy, right? 5 times ReLU of x plus 1. Then we have minus 5 times ReLU of x. Then we have 5 times ReLU of x minus 2 plus 5 times ReLU of x minus 2. I'm so sorry for using R and RE, but please consider that they are both the same thing. I'm just making this mistake while writing. Then plus 15 times ReLU of x minus 3. Is this our function that we had? We had minus 20 times ReLU of minus x minus 1. That is here, this guy. Then 5 times ReLU of x plus 1. We had that. 5 times ReLU of x plus 1, right? This guy. Then we have minus 5 times ReLU of x. We have that here. So minus 5 times ReLU of x. Then we have 5 times ReLU of x minus 2. That is this guy. Then 15 times ReLU of x minus 3. That is this guy. So now what you really see is this neural network with these weights and these biases and ReLU as the activation function can actually approximate what we have, the continuous function that we originally selected. The function was minus, it's here in this x cube minus 3x square plus 2x plus 5. These set of ReLU functions, if we add it up, it can very well approximate our function. Of course, as I mentioned earlier, if you want better accuracy or more precision, you can add more ReLU functions. You can chop up the function into more and more discrete pieces. So let us go back. Did we really demonstrate the universal approximation theorem here? The universal approximation theorem states that a feed-forward neural network with a single hidden layer containing finite number of neurons can approximate any continuous function on a subset of inputs to any desired degree of accuracy, provided the activation function is non-constant, bounded, and continuous. Did we satisfy these things? It's very now it does not look very complex anymore, right? So we had a feed-forward neural network, right? It was feed-forward purely, correct? We had a single hidden layer, right? Then we had finite number of neurons. How many did we have? We had 5 in the hidden layer. We had a continuous function. It was x cube minus 3x square plus something plus 5, right? That was a continuous function. And we had non-constant, bounded, and continuous activation function. What do we mean by bounded here? The boundaries are from minus 2 to plus 4 in our case. Non-constant, obviously, because we are using ReLU. ReLU is not constant. Is it continuous? Of course, it is continuous. So we have satisfied all these conditions. And now we are able to approximate the function that we originally selected. So let me just write it down here so that you know the feed-forward neural network part was correct. Single hidden layer. So number of hidden layers was 1. 5 nodes within the input layer. Continuous function. Yes, it was a continuous function. X cube minus 3x square. This was the function, right? Square plus 2x plus 5. So this is a continuous function, and we were using ReLU activation functions to get the approximation. So this wonderfully shows how we can demonstrate the actual universal approximation theorem using a very simple example. So when does the universal approximation theorem, when does it not work? So as you saw, it works only in a defined range of input. So what do we mean by defined range of input? In our case, it was from -2 to +4, right? X values from -2 to +4. And we saw that here. Here between -2 to +4, this graph looks like good. The green color piecewise linear function is approximating our function really well. But if I zoom out, and if you can see more number of points from, let's say, a range of -10 to +10 or something like that, you can see that there is complete divergence. The green plot is not at all matching with our original function anymore. So the range has to be limited, or it has to be defined. We have to train the neural network to within the range. If a new range comes, the neural network has to be trained in that range to have good weights and biases. We may have to also increase the number of nodes in the hidden layer if we have to accommodate more range. And if there is a non-continuous function, we might need more than one hidden layer, correct? Okay, now one more thing before we conclude the lecture. Do you really understand the significance of activation function? Like, the reason why neural networks can approximate even these complex nonlinear functions is because of the activation function. What happens if activation function was not there? Let's take a look at this, right? So let us go back to our graph. Let's say this was R of x equal to simply x. This was simply x instead of ReLU of x. Then what would happen if I just plot R of x equal to maybe max of x? Okay, I know why this issue is happening. It's because, sorry, it's not x, it's just z. R of z equal to z. And now do you see what's happening? I have added bunch of complex functions. These are all straight lines, right? Because R of -x minus 1 is -x minus 1. So these are all linear functions. And no matter whatever I do, if I add bunch of these linear functions together in whatever way we want, by changing its slope, intercept, whatever, as long as it's a straight line, a combination of these straight lines will give me another straight line only. So if we don't have the ReLU activation function or any kind of activation function, we cannot represent nonlinear data using neural networks. This is why activation functions are so important. And I would even say it's the cornerstone of the whole idea of neural networks, that you can construct these piecewise functions and approximate pretty much any function that way. If you have discontinuous function, that is the reason why sometimes you have multiple hidden layers. So I hope this makes it very, very clear for you in a visual way, the importance of activation functions. And with that kind of insight, I think we can wrap up the lecture here. Thank you so much for listening. I hope this lecture brought some clarity into you, not just about universal approximation theorem, but also about the general concepts behind and the general intuition behind the usage of neural networks. We'll be coming up with more lectures which are relevant to machine learning concepts from many different subsets of machine learning. So stay tuned to that. Until then, see you. So bye.